Hey, welcome to week 5. We're going to have a lot to cover this week, and we're going to start by talking about, we're probably going to break up these topics into a couple of different videos. So the first topic we'll talk about is linear approximations. Okay, so the idea is that suppose that we have a function that is complicated, and we want to approximate it using a simpler linear function. So I think a good picture is this one. Let's say that this f of x function is complicated, say an inverse tangent or some kind of a log or a trig function, and we want to kind of essentially use another simpler function, this red line, a linear function, to approximate it. Linear functions are the simplest kind of function, and for a lot of the example that we'll see, these linear functions are good enough to approximate much more complicated functions f of x. And the idea is that we just need to have a point, a f of a, on the original f of x, and then if we know the slope of the tangent line, in fact this linear function L of x is the tangent line. So we're using the tangent line to approximate the function. So we need to know the derivative of the function at this point. Then we can find the equation of the line, because the line is defined by the point and the slope. And so if I know the slope, or if I know the derivative of the function at a, which is f prime of a, then this equation right here is the point slope form of an equation of a line, and so for example, the point we're looking at is a f of a, and so the linear function is given by f of a plus f prime of a times x minus a. Again, this is just an equation for, if you remember from pre-calculus, when you first learn about lines, when one of the equation of lines that we have is, if I know a point, a f of a, and I know the slope, then that's enough for us to write the equation of the line, and that equation is this one. And so the linear function L of x is simply f of a, that's the point, plus the slope f prime of a times x minus a. And so this is called the linearization of the function at a. Again, this is not supposed to be complicated, in the sense that this is exactly the same thing as the tangent line. So we already talked about tangent line previously. If I can find the equation of the tangent line, I can use that tangent line to be an approximation for my function f of x. So in other words, f of x is approximately L of x, where L of x is the tangent line. So if x is close to a, if I'm on the function and I'm close to a, which is the point, then the function and the tangent line are almost the same. They're basically the same. So that's what this says. The function, which is complicated, is basically the same as the tangent line, which is a lot simpler, and this is the tangent line at the point a f of a. Okay, so here's a good example of that. Suppose that we have a function which is a little bit complicated. This is the square root function, square root of x plus 3, and we want to find the tangent line approximation to this function at the point a is 1. And then we're going to use that linear approximation to approximate root of 3.98 and root of 4.05. So the first thing is we have to find the tangent line to this function at this point a is 1. By the way, when you plug in a is 1, you get root of 4, which is 2. So when a is 1, this is this part right here is 4, and notice that this is why we can use it to approximate root of 3.98 and root of 4.05, because notice 3.98 and 4.05 is very close to 4. So again, approximation only works when you're close to the point. And so yeah, the first thing we're going to do is we're going to first find the tangent line of this function f of x at this point a. So first we have to differentiate f of x. This is just a power rule, right? And normally this is also the chain rule because there's an outside and inside function. But the inside function is linear, that has a 1 here, so it doesn't matter too much. So let's try it out. So you bring down the 1/2, subtract 1, 1/2 minus 1 is negative half. Then technically you have to differentiate the inside, but when you differentiate the inside you get 1, because the derivative of this is just 1. So that's just the chain rule, but in this case it just gives you 1. And so again, to make the negative, this is a negative exponent, so you can make it positive by bringing it down to bring this whole thing down to the denominator, and so it becomes positive 1/2, which is the same thing as square root. So this is f prime of x. We're looking for the tangent line, so we have to plug in the point a is 1. So when you plug in a is 1 here, you get that f prime of 1. When a is 1, this is a root of 4 is 2, so it's 1/4. So the slope of the tangent line is 1/4. So we know the slope, we know the point, f of 1 is 2. Again, when you plug in 1, you get 2. So you know a point and a slope, so that's enough to give you the equation of the line. And that's what this is. This is the tangent line using that point and that slope. So f of 1 is 2, f prime of 1 is 1/2, or 1/4. And then x minus a is x minus 1. So after simplifying this, again, this is just the tangent line, right? This L of x is just the tangent line that we learned previously. The tangent line to this function at the point a is 1. So now we can use this tangent line to approximate this function. So in other words, the function f of x here is approximately the tangent line, as long as you are close to 1. Because 1 is the point where we find the tangent line. So if x is close to 1, like 1.01, 1.02, 0.98, the tangent line and the function is very close. And so for example, when x is 0.98, which is close to 1, when you plug in 0.98, you get root of 3.98. And we know that this is very close to the tangent line. So instead of doing this square root, which is hard, we can use a simpler, much simpler function, which is a linear function. So again, square root is hard to do. For example, if you have to do this by hand, I can't do a square root, but I can even by hand, by pencil, I can do an equation of a line, and these are basic operation: dividing, adding. And so that you can do by hand, but on the left side you cannot do that by hand. That's a little bit harder. And so to approximate this, I use the tangent line to approximate, and I get 1.995. So 1.995 is a tangent line approximation to this. In the same way, if x is 1.05, so that's close to 1, you plug in 1.05, you get root of 4.05. So again, we're going to approximate this using our linear, our tangent approximation. So again, the left side is hard to do. The right side, if I have to, I can do this by hand, by a pencil. And I get that this is the approximation for this value. Turns out that in the past, when the calculators first came out back in the 60s, 70s, the square root symbol was in some of those basic calculator. And so one way to do the square root is to kind of use this linear approximation. So here's the picture of that. Notice again, right? Here's the square root function, square root of x plus 3, and notice the tangent line approximation. If x is close to 1, right? We saw that 1.05 or 0.98. If I'm close to 1, the red line and the blue function, they're basically the same. They're so close. If you far away, if you over here, then notice that the error here is bigger. So maybe the line is not as good an approximation to the curve. But if you close by to 1, they're basically very similar. Okay, maximum and minimum values. So here's a function. Here we want to look for something called the absolute maximum. Notice this point right here, that when x is 3 and y is 4, this is the biggest value of the function, and this is the smallest value. So we call these the absolute maximum and the absolute minimum to the function. So this is the absolute maximum. It's not just the maximum, it is the absolute maximum. And this is not just the minimum, right? It's the absolute minimum. Later on, we're going to talk about something called local minimum, and that's going to be a little bit different. But right now, these are absolute maximum. These are the absolute biggest value, and this is the absolute smallest value. And another distinction, well, there's also another kind of maximum called local maximum, and another minimum called local minimum. And a value f of c is a local maximum if f of c is bigger than f of x, but only if you are near c. So maybe f of c is the biggest value, but only if you're close by to for all the x value that's close to c. And same thing for local minimum, in the sense that this is not the smallest value on the entire domain or interval, but it's the smallest value if you're close, right? If you're close to, if x is close to c. So let's see some picture to kind of explain this. So let's talk about both absolute maximum and local maximum, and then absolute minimum and local minimum. So for example, look at this value up here. When x is d, f of d, this is the absolute maximum. No other value is bigger than this. How about look at this one? When x is a, f of a, this is the absolute minimum. There's no value that is smaller than this. Right, so those are absolute maximum, absolute minimum. Let's look at this one right here. This one is not the absolute minimum, right? It's not because this is smaller, but it's a local minimum. It's smaller than things close by. If I'm close to C, if x is around C, this neighborhood of C, then this is the smallest value in this local area. Same thing, this is not the absolute maximum, because this is bigger, but this is a local maximum. It's the biggest value in this neighborhood, right? If I'm close to B, this value is the biggest if I'm in this little area. Again, this is another example of a local minimum. It's not the smallest value. This is smaller, but it's the smallest value if I'm close to E. If I'm in this small neighborhood, this is kind of like a valley, right? This is the local minimum in this area. Yeah, so this is another example here. When here's a function. If I'm looking at only from -1 to +4, right? Notice that this is not the absolute maximum, right? Because this is much bigger, but it is the local maximum. If I'm close to 1, this value is the biggest. This 1 value is the biggest. And then notice that this right here is an absolute minimum, right? It is not only it's also a local minimum, right? It's the smallest value in a neighborhood of 3. If I'm close to 3, this is the smallest. But in fact, this is the absolute minimum. It's the smallest over the entire interval from -1 to 4. And then something else that we sometimes will say is that when you have an endpoint, right? This right here, for example, this is not the absolute maximum. This is bigger, but it is a local maximum, right? If I'm notice that the function is not defined outside on the right side of 4, but if I'm around 4, on the left side of 4, this is the biggest value. So it's the local maximum. And notice that there's some function that has a this is an absolute minimum, but this function, if I extend both ways, has no maximum. This will go forever this way, forever that way. So it's possible that we don't have absolute maximum. And here in fact we have no absolute maximum. This go forever up, so there's no absolute maximum. There's also no absolute minimum, because this will go down forever. So it's possible that we don't have these absolute max and min. This theorem is called the extreme value theorem. It can't basically tell you when we're guaranteed to have an absolute maximum and an absolute minimum, because again we saw an example where we don't have that. But this will tell you when we have absolute max and absolute minimum, and this turned out to be very useful in a lot of the application we'll see. And so here's the condition: if you have a function f is continuous on a closed interval, so if my domain is closed, including endpoints a and b, and my function is continuous, then I'm guaranteed to have an absolute maximum f of c and an absolute minimum f of d for some values c and d inside the domain, the closed interval domain. So again, assuming that f is continuous on a closed interval, this guarantee that we have an absolute maximum, guarantee that we have an absolute minimum. So for example, here it is, right? Here we have closed interval, continuous. So this is the absolute maximum, this is the absolute minimum, guaranteed to have it. Here's another one, closed interval. This is the absolute maximum. Notice that the absolute minimum is actually at the endpoint here. This is the absolute minimum. And then here's another example, closed interval, continuous. The absolute maximum is here, and also here as well. The absolute minimum is here. So a continuous function on a closed interval, guaranteed to have absolute max and min. This is important application because sometimes we want to, before you try to find the absolute max and min, we want to know that they exist, right? For example, when I'm looking for the absolute maximum profit, I like to know that it exists before I try to find it. Maybe I want to try to minimize some kind of cost. So I also like to know that there is an absolute minimum cost before I try to find it. So this theorem is useful to kind of give us confidence that we do have those values. Now, if our function is not continuous, then this theorem does not apply. So this function is not continuous. Notice it has absolute minimum, but it doesn't have an absolute maximum. So again, we may have it, we may not have it. But in this case, we don't have an absolute maximum. We don't have a guarantee that we cannot guarantee that it has it, because the function is not continuous, so we cannot apply the theorem. This is an example where, again, the function is not continuous. Right? There's a hole here. There's a vertical asymptote. Notice this function has no absolute maximum. There's no absolute maximum, and there's no absolute minimum. So for the theorem to guarantee absolute max and min, we have to have that the function is continuous on a closed interval. This is continuous, but it's not continuous on a closed interval because this is a hole here, right? It's not. We have to have a dot here to be continuous, it has to include the endpoints. It's not continuous here, so we don't have endpoints. So that's why we have that problem. This is a Fermat's theorem. It says that if a function has local max and local minimum at C, then f prime of C exists, then it must be 0. So again, not absolute max or min, but if you have a local max or local min, and we know for sure that the function has a derivative, then this theorem says that guarantee that derivative must be 0, right? But we have to be careful because it's possible that we have a local or an absolute minimum without the derivative being 0. So just because the derivative is 0, that doesn't mean that it's a local max or min. For example, here we see that the function has no derivative, right? This is a corner, so it's not differentiable. So just because you have a local maximum min doesn't mean that f prime is 0. This just says that if it is a local maximum min and f prime exists, then it must be 0. Right, so this case f prime doesn't exist, but if it exists, it has to be 0. So here comes a very important definition because of those previous couple examples. So notice that, right? We know that if it's local maximum min, either f prime is 0 or f prime does not exist. So here's so those points are very important points. We call those critical numbers. A critical number of a function is a value xc in the domain such that either f prime is 0 or f prime at that point c does not exist. And these are critical because these are candidates that give you local max or local min. So if something is a local maximum or a local minimum, it has to either be f prime is 0 or f prime is undefined. So when we find these critical numbers are the numbers where we might find maximum and minimum. Okay, so let's do some example of finding critical numbers. How do you find critical numbers of this function f of x? This is a simple cubic function, where you just differentiate it and solve for 0. Right? Well, it's either solve for 0 or solve for where it's undefined. But because this function is polynomial and f prime is polynomial, we're never going to have undefined problem. So we should just try to solve for 0. So notice if I factor things out, the two zeros, f prime is 0 when x is either 0 or when x is 2. Right? Try and solve for 0. So 0 and 2 are the two critical numbers of this function. Again, why are these critical numbers? Well, they may or may not give rise to maximum and minimum. So we'll see that a little bit later. Okay, the second example is that this one is a little bit more complicated. This is the product rule. So let's do that. If I apply the product rule, I get, again, the product rule says that keep the first, differentiate the second, plus keep the second, differentiate the first. So keep the first, differentiate the second is -1. Keep the second, differentiate the first is just the power rule. Bring down the 3/5, -1 is -2/5. And so doing a little bit of algebra, again, this is a negative exponent, so you can bring it down to the bottom, for example. And then we're going to find a common denominator between these two, and then combine this fraction with this one. This is over 1, so the common denominator is just basically this. So if I multiply top and bottom of this by this expression to make it the same denominator, I get this. So we multiply this on top to get -5 x to the 2/5 times x to the 3/5 is just x. So that you get this. And then now you have a common denominator. You can combine them. The top part you can simplify and you get this. And so this is f prime. So again, if I'm looking for the critical number, I want to know whether when this is 0 or when it's undefined. Well, this is 0 when you have a fraction like this. This is 0 when the numerator is 0. So if I solve for 0 in the numerator, I get x is 3/2. Solving for 0. So 3/2 is a critical number. So that satisfies this first part. If f prime is 0, then it's a critical number. But notice that you have an expression here where you can have this being undefined. If you have a fraction like this, it's undefined when the bottom is 0, the denominator is 0, and that's happening when x is 0. So when x is 0, f prime is undefined, and that's another condition to get a critical number. So in this example, critical number happen when the numerator is 0 or when the denominator is 0. And so the two critical numbers are 3/2. Again, 3/2 makes the numerator 0, which means the slope is 0. And then when x is 0, f prime does not exist because you're dividing by 0. So those are two critical numbers. Now I want to clarify something here. When x is 0, this is undefined, but notice when x is 0, it is defined in the original function. When x is 0, when you plug in 0 here, there's no problem. And that's important because in this definition, c has to be in the domain of the function. So in other words, when you plug in c into the function, it has to be defined. It cannot be undefined. And so again, 0 is a critical number because it is undefined in the f prime, but it has to be defined in the original f. Because if 0 is also undefined in the original f, it's not in the domain, and we don't care about things that are not in the domain. Okay, so here comes a very important the thing that kind of ties everything together. If I'm looking for local maximum or local minimum, then I can only find them at critical numbers. So this is important. Now, just because something is a critical number, that doesn't mean it gives you a maximum min. But this theorem says that if you have a local max or local minimum at c, c must be a critical number. In other words, to find local max and local min, we look at all the critical numbers, and again, not all of them will give you local max or min, but if they are to be local max and min, it must come from the list of all the critical numbers. So that's a little bit confusing. So let's do an example. We have to do an example in a moment, but before we do that, let's talk about this tying back to so this is local max, local min, but this is also absolute max, absolute minimum. So here's kind of the theorem that kind of help us find absolute max and absolute min. So we need the function to be continuous on a closed interval. Again, earlier we have a theorem called the extreme value theorem. So this is why we need that. So we can find absolute max and absolute min by first finding critical numbers. Again, the reason why critical numbers is important because critical numbers may give you local max and local min. Again, local max, local min may be absolute max, absolute minimum. So you want to look at critical numbers for some possible local max, local min that might turn out to be absolute max, absolute min. But we also have to check the endpoints as well. And so between the critical numbers and the endpoints, we in those lists we guarantee to have an absolute maximum and absolute minimum. In fact, the biggest of these, whatever value from critical numbers and endpoints that is the biggest, that will be our absolute maximum. And whatever is the smallest of this is the absolute minimum. Going back to some of the example earlier, right? We saw that, notice here in this example, the absolute minimum is actually at a critical number. And then here in this example, the absolute minimum is at an endpoint. So critical numbers, right, can usually give you local max, local min, but they can also give you absolute max, absolute min. But notice in some cases, the endpoints might actually give you the local max and local min. So that's what this is saying. This is saying that to find absolute max, absolute min of a continuous function on a closed interval, we look at critical numbers and also endpoints. Okay, so here's an example. We're going to try to find the absolute max and min of this function on a closed interval. Notice this is continuous on a closed interval. So we have to find critical numbers and also check the endpoints. To find the critical numbers, we have to differentiate it. But we did this earlier. This is one of the early examples we did. We found them to be 0 and 2. Again, in the previous slide, we did that a couple of slides earlier. So these are critical numbers, 0 and 2. That's where the f prime is 0. But I noticed that because this is a polynomial, we don't have f prime being undefined. So those are critical numbers. And also there's also the endpoints, negative a half and also 4, that's the endpoints. So between the critical numbers and the endpoints, we guarantee to find absolute maximum, absolute minimum. So what we do is we plug in the critical numbers and the endpoints into the original function and see what we get. You plug in 0 into the original, you get 1. You plug in 2, again these are critical numbers, these are the middle numbers, you get negative 3. You also check the endpoints. Plug in negative half, get 1/8. Plug in 4, you get 17. Between the critical numbers and the endpoints, we must have our absolute maximum and our absolute minimum. Notice here, 17 here, that is actually an endpoint. That is the absolute maximum value of this function on this interval. And then the negative 3, that's the smallest value. And notice that this is amazing, right? Because we're trying to find the absolute maximum on this whole interval. So there's an infinite possibilities here. But this process, the calculus, we don't have to check every single point in this entire interval. We only have to check 4 points: critical numbers and endpoints. And that's enough to know that this is the biggest value in this interval. This is the smallest. So here's a graph of that, right? Notice that the local minimum, the critical point, gives us also an absolute minimum, but the absolute maximum happens at the endpoint. Okay, so the next part is the mean value theorem. This is actually one of the most important theorem in calculus. It actually gives us a bunch of very important results that we'll see later. So this is the mean value theorem. Okay, first of all, we're going to cover kind of a special case of the mean value theorem called Rolle's theorem. So again, the mean value theorem includes this case, but this is kind of a special case that's helpful to kind of isolate from the mean value theorem. Suppose you have a function, and this function satisfies the following 3 hypotheses. It's continuous on a closed interval. It's differentiable on an open interval. So it's differentiable. We don't need it to be differentiable at the endpoint, but we need it to be continuous at the endpoints. And the last condition is that f of a is equal to f of b. The endpoints have the same y value. Then this theorem, Rolle's theorem, guarantees that there's a point somewhere in the middle between a and b such that f prime at c is 0. So let's look at some pictures. I think that's the easiest way to kind of understand this theorem. This theorem says that if you have a continuous function, these are continuous, and the endpoints have the same value. Notice f of a, f of b have the same value. F of a, f of b, same value. F of a, f of b, same value. F of a, f of b. So all these cases, the endpoints have the same y value. This theorem says that if it's continuous and differentiable and have the same value at the endpoints, somewhere in the middle, there has to be a place where f prime is 0. In other words, there has to be a horizontal tangent. In fact, there are 2 here. There's only 1 here. In fact, there's infinite value here. Every point here has the slope 0. And this makes sense, right? Because if you have the 2 endpoints have the same value, if this goes up, it has to come back down. When it comes back down, it'll have slope 0. Right? Whatever goes up here has to come down. Okay, so that's a special case of mean value theorem. And let's kind of apply it to an application. Let's say we have a position function, f of t, of a moving object. So say an object go left or right. And let's say that the object is at the same place at 2 different places. So at time A and at time B, the object is at the same position. Rolle's theorem says that there has to be some time C between A and B such that f prime of C is 0. And that makes sense because if f is the position function, f prime is the velocity function. So Rolle's theorem says that there has to be some place where the velocity is 0. And that makes sense because if you add a position, if you add the same position at 2 given point, then let's say that you leave the position, follow my mouse, right? You have to stop and come back, right? And so Rolle's theorem guarantee that you have to stop at least once, because if you at the same position, either you stay there the whole time and have slope 0 and have velocity always 0, or if you leave it, you have to stop and turn around and come back. This is also true if you throw a ball up in the air. So if your ball is in your hand, which is at the same position, you throw it up, and when it lands in your hand again. So that means you have the same position at A and B. So somewhere along the way, you have to have f prime being 0, and f prime being 0 means this velocity is 0. But we know that if you throw a ball up, it has to stop at the top and then go back down. So where it stopped at the top is where the velocity is 0. This slide is an optional slide. It won't be tested. If you want to read it, you may. It's optional. This is using Rolle's theorem to show that something has a function has at most one root. If you remember that we did the intermediate value theorem. In that theorem, we know that we can show that there's at least one root. Rolle's theorem allows to show that there's at most one root. Again, optional. You can read it if you like, but won't be tested. Okay, here comes the main mean value theorem. Again, Rolle's theorem. In a second, we're going to see Rolle's theorem is actually a special case of this. So this theorem includes Rolle's theorem. So here's the general version of Rolle's theorem. Again, we need a function to be continuous on a closed interval, differentiable on an open interval. But now we don't have the actual assumption that the two endpoints are the same. Here, the two endpoints can have different value. So mean value theorem says that there is guaranteed to be a x value called c between a and b, such that f prime of c is equal to fb minus f of a over b minus a. This looks very confusing, but it turned out to be not so bad. So I think the best way to explain this is to kind of do this graphically. The right side has a simple interpretation, and so is the left. And this theorem guarantees that there's at least one c where we can have this happen. So let's explain this a little bit more visually. Okay, look at the right side here. F of b minus f of a over b minus a. Let's look familiar. F of b minus f of a, so that's the rise, the change in y, divided by b minus a. That's the change in x. So the right hand side is actually exactly the slope of the line joining the two endpoints. So look at this one. The line joining the two endpoints, the slope of that blue line, that's on the right side. The left side is the slope of the tangent line, or the derivative at a certain point. So this is not this is slope at a specific point. And this theorem guarantees that there has to be somewhere in the middle where the tangent line have the same slope as the endpoints. So you can see here that works. Here the endpoints. This is called the average slope. The mean value theorem guarantees that there has to be one place C where the tangent line has the same slope as the line connecting the endpoints. In other words, the instantaneous slope, somewhere along the way, there has to be a place where the instantaneous slope has to equal to the average slope. So same thing here, right? You connect the dots between A and B, the endpoints. You have the average rate of change. This theorem guarantees that there has to be at least one place. Here in this example, there's actually two places, but there has to be at least one place where the instantaneous slope, or the derivative, there has to be at least one place where the derivative is equal to the slope of of connecting the endpoints. And so let's kind of explain why this is useful. Suppose that we have, again, you're driving along a road, right? You're going left to right. Your position is S. Then the interpretation of the slope of the endpoints is your average velocity, right? So again, if this is position, then this slope is changing position over changing time. That's exactly the average velocity. So that's the right hand side. So the left hand side says that there has to be a place where the instantaneous slope. Remember, if this is velocity, the instantaneous slope is the the velocity at that point. So this mean value theorem guarantee that there has to be a place somewhere where your velocity is equal to the average velocity. So in other words, if you're driving, there has to if you're driving on a road trip, your average velocity, right, is this value. The theorem guarantees that there has to be at least one moment in time where your velocity, your instantaneous velocity at that moment, equals your average velocity. And that makes sense, right? Because if your average velocity is a certain value, you must have traveled that average velocity at least once. Because if you never travel your average velocity, let's say you're always above the average velocity, then your average velocity would not be would be higher. So that doesn't make sense. So if you're always traveling below the average velocity, then the average velocity cannot be that value. So it has to be one place where you travel the average velocity. Here's another one that's optional. Again, you can read it. This is to use the mean value theorem to kind of find a bound for a function. So help you kind of find the possible either upper bound or lower bound for a function. And then here's kind of the last slide for the first video. Again, we're gonna have 2 videos this week covering the material. This theorem says that if f prime is 0, by the way, both these theorems are consequences of the mean value theorem. Again, we won't cover the proofs of this, but if you use the mean value theorem, you can find you can prove these theorem. So this says that if a function is if you have a function where f prime is always 0, then that must be the constant function. The constant function is one where it's horizontally. It's always going on. It's always the same value. So so again, if the function is constant, it's obvious that slope is always 0. But this is not obvious. If you have a function where the slope is always 0, it must be the constant function. And here's another result. If you have 2 functions with the same slope everywhere, then the 2 functions must be the same up to a constant. So let me say that again. If you have 2 functions which always have the same derivative everywhere, then the 2 functions are basically just vertical shift of each other. In other words, one function f of x is the other function plus a constant. So f is just the other function move up or down by a constant c. And that makes sense, right? Because if you take a function and move up and down, all those functions have the same slope. Okay, that's it for the first video.